Hi guys. One presumes you took a look at the pre-lab assignment, and so I can put this clock here. Yeah, I can't believe it's 4:30. I could scream. Just wasted a lot of time working on this. The original lab manual is really, really bad. Okay, so let's just go over it. I wrote a little intro in the pre-lab assignment, and so normally I would spend more time in it now, but I'm so tired. So you have this Bernoulli's equation, and so it takes into account various things, and it's about fluid flow, and it's incompressible. It turns out that air is an incompressible medium. Like when you calculate, you can use Bernoulli's equation or corollaries of it for calculating airflow and such, and especially people who work in designing airplanes are very wonder they use these things, especially the equation of continuity actually is what's used to it's why how airplane wings generate lift. It's not just because they angle it a certain way. It's because if you look at wings, except for airplanes like jet fighters that go above the speed of sound, an airplane wing is curved on the top and flat on the bottom. And then that produces lift because of Bernoulli's principle, and in particular the equation of continuity there, which just says that any if you take the area times the speed, if you think it kind of, so you have area is meters squared, right? And then velocity or speed is meters per second. So you notice it's volume per second. And so it basically means any volume of material coming in some area has to equal the volume flowing through another place. So it just means that whatever goes in has to come out, and there's no external sources of fluid. You can't have something like, you can imagine simply a hole in the pipe, or you can't spontaneously create fluid in the middle. But which sounds kind of dumb. Of course, that's true, you would say to yourself. But writing this out allows people to do many simple calculations. Equation 2. Now, because the pressure is the same, we talk about the pressure we're picking the surface of the liquid, and we're picking the if you'd like, surface here as it comes out of the little spout here. Of course, in this case, it's going to sit here because of gravity, and in this case, the liquid's just going to come shooting out, but it's also going to fall because of gravity. And at first glance, you might think that this was, in fact, this is, sorry, never mind. Let me look this over for a minute. Yeah, this is simply taking equation 1 and rearranging it. So you can cross out the P's, and I finish, yeah, it says atmospheric pressure at both places. So you can cross out the P's, you can cross out the rho's because it's the same liquid, and then you're left with the half, the V squareds, H, and G. So it's pretty simple to recreate that. Equation 4, it's not very well explained, but what happens is, using the idea of a drop ball, if I know R, I can calculate the initial velocity in the horizontal direction, because it's simply whatever that velocity is times time, right? And what's the time? Well, if you'll forgive me, time and time again, you always get the the time from the y coordinate. So if you drop something from a height, the time it takes to fall is just the square root of 2 times the height over the acceleration of gravity. We've done it over and over again. So in this case, we're going to measure r, and notice I put in our average. So we're going to be measuring r's, and we're going to use a spreadsheet for our average, so don't sweat that. And then we just multiply it by that. And this is how we get V2 on the spreadsheet. Okay, so like you read here, a conductor, spotters. So I imagine what's going to happen is that someone is going to probably say ready, steady, and open the valve. And then somebody should watch a liquid level and say, hey, it's at 15. Like mark, somebody else hits their stopwatch. I can see a variety of ways of doing this, and we can work it out together when in class. This and you've done something similar before, but we've had those timing. We've used the photo gates that were connected to that black box that had the triggering mechanism, so that made it a lot easier. Now we're going to have to just rely on so-called Mark 1, meaning the first iteration, the first model, eyeball, and our wits, and working together so we can reduce error. And in this case, we're not going to do plus or minuses, I imagine eventually, but again, I had to spend so much time trying to understand this stupid lab. So one of the things to look at here in figure 1 is this idea of, we see we're little h with no subscript. So to make our lives easier, this line through the center of the spout is going to be our reference point. And apparently, and I haven't seen this equipment, but apparently the numbers for h on the side of this beaker are actually RH. The 0 passes through the spout, so the orifice. Okay, so that just makes our lives easy. So though I went ahead and I made this other sketch, and you please feel free to use it. So you have to determine where, in a sense, it's x sub 0, right? So x sub 0 is here, and we got to use our plumb bob to find it in the bottom of the sink. And then once you do these things, we got to make sure this apparatus doesn't move. Now again, I don't know what it's going to look like, so I can't predict how we might do that. And then you can record this little h is pretty easy. It might be a little more challenging to measure capital H, but you measure that once, you write it down, and good practice is to check it once in a while. And then the manual says to lay a ruler down, and then you can watch the liquid hit. Now what's going to happen is that as the liquid goes down in there, we're going to notice that it's not going to shoot out as far, because remember that the thing making it go down is gravity. There's also a pressure down below, and that's going to change, but we don't have to worry about it. And let's see, V2, right. So one can imagine little h, you notice it has a dependence on well, let's see, let me think about this. There's no time, you see there's no time dependence in here. Okay, that's the rub here. Sorry, I'm pretty tired, but I wanted to get this done so I can relax. So one thing is, if you look at, don't even look at the original lab, but it took me forever to figure it out. We're not measuring, we're going to measure R as a function of H. And in this case, we need to pick a particular set of H's. and they're here. So the numbers on the left here are ones we're going to use. The rest of these are kind of like numbers I kludged together, and they're not necessarily right. But we definitely want 15 down to 4, and I think we can do it in 1 centimeters. So the first part, procedure number 2, we're going to set the water going, and then we're going to have spotters are going to say, hey, it's at 15, and then another spotter is going to write down R, whatever they see, and then 14 down the line. So it's going to be a little tricky, but at least they don't actually have to measure the time. You could, and if you did, then that's doing it all at once, and you guys can think about it, but I think in practice it might be a little difficult. Now, the normalization comes in because when we're going to use the same set of H values, so we have to be careful, and I think that when we fill up the beaker and let it go, we're going to notice it doesn't go shooting down really quickly, because when I looked at the sample data, it took 11 seconds to go 4 centimeters. So this is 1 centimeter in 5 seconds. That's not too bad. And there's ways of figuring out how to determine that. And boy, and I just thought of one. Oh my goodness. Yeah, but we need a time lapse. I have to talk to you about my mom used to be a computer at Grumman Aerospace. And I just realized, but you know, this time around, maybe we're not going to do it. I don't want to burden you guys with too much. And we won't write a report for this one either. Okay. So, take a look through here. And I tried, after I'd written a lot of this, then I realized later on exactly what they wanted in part 2. And I tried to clean it up. There may be some things that don't make sense in there anymore. Then the next thing is we're going to refill it and and then carefully time it at each one of the 15, 14. And for example, one idea I think is that you fill it up past 15, and then somebody opens the valve, says ready, steady, go, and you start the timer, and then you hit the timer. Somebody says mark 15, you write that time down, and then write down the line. So you don't really have to make sure that that point. Notice here that there was 0, and that doesn't necessarily have to be 0, right? We've dealt with this before, so that's no big deal. Okay, let's think. Yeah, so if we're careful and we use a set of H values that are common in part 2 and 3, then we can deal with our data analysis. And then the other thing we'll have to do is just measure the diameter, inner diameter, think about that one, and the inner diameter of the orifice. And notice, I think I copy-pasted the latest version of this. Yeah. So I'm giving away a hint there. Too bad, I should have realized that, but that's fine. I didn't do everything, and I'll go over all these entries in another video. I just wanted to make sure we're ready. So you'll see they want us to do an analysis. Yeah, use the spread, all kinds of things. I started trying to make a list, and it's like, oh, jeez. I mean, you could at least, if you like, start at least creating the headings. And if you should remember how to do T average, and H, we're going to use H average because we're going to see how from 15 to 14 we have 5 seconds of time, and so we can calculate how fast the level went down by taking delta height over delta t, which remember is the average speed over that interval. So what we've done in the past is we've picked the t average as the center of that time bin, and now we're also going to pick the H as the center because we have to make plots of this one here. The x-axis is H, not time. So that's all we need the H average for. We don't use it in the delta H over delta T. We use the raw delta H. But remember, this is all about if you have some kind of shape, if you make your interval small enough, you assume that it's a straight line. It doesn't have to be flat. It's just a straight line. And then we can calculate a delta, say delta rise over run, the slope basically over that small interval, and we assume the average value is the value. And when you do have that interval, it's sometimes called a bin, or it's many times called a bin. We always say that if it's the center of that bin is the value, we know that the value we get for V is the average of the endpoints in time and space. And then when we want to graph it, the practice is once again you're using the time at the center and also the H at the center, depending on what you're doing with it. And so to be consistent, I also have R average here, and I'll go over that another time. But in case you guys want to jump ahead and get started, and I think you should, because we'll go over it as much as we possibly can in class. Okay, so I'm going to stop this now, and then I'll make another one and talk a little bit about the analysis.